All right, so from yesterday we did two-step conversions that integrated conversions using Avogadro's constant while simultaneously using molar mass. So I'm going to go ahead and take a second and work through the three practice problems so you can check how you did with yours and make sure that your solutions are correct. So in example 1, it asks how many grams, so I know that I'm solving for mass, and again the unit would be grams, and it says that are found in 2.3 times 10 to the 24th atoms of silver. So I know that this is going to be a two-step problem because I don't have a conversion factor that relates atoms to grams. So when I go ahead and set this up, I'm going to take my given of 2.3 times 10 to the 24th atoms. Based on what I have with my map, that means the only place I can go is I need to use Avogadro's constant, 6.022, times 10 to the 23rd atoms is to 1 mole. And I know based on my given that atoms must go in the bottom, so they cancel out. I know that I'm not done because the problem is asking for grams. Again, to get grams, we need molar mass. This part is pretty easy because we're working with just an element, so the molar mass is what's provided on the periodic table. So if you find silver, it's 107.87 approximately grams per mole. Again, for setup, I have moles in the top, therefore moles need to go in the bottom, and the 107.87 should have went in the top. For an answer, I got 411.99 grams of silver. Again, for yours, as long as it's in the ballpark of being relatively close to that number, we may have slightly different answers just due to rounding. So if you're unsure on something, feel free to reach out and I can confirm if the answer was correct or not, or rounding issues were a factor or not. So we have two more examples to take a look at. So in this next one, the given is the 450 grams of sodium sulfate. So right off the bat, because I'm starting with grams, the only thing I can do to move forward is I need to calculate molar mass of it. So the molar mass is based on our formula here. So I have sodium, and there are two of them. On the periodic table, rounding, it's 22.99. We have one sulfur. On the periodic table, it's 32.07. And finally, we have 4 oxygen, which again rounds to 16. Multiplying and adding them all up, you get somewhere approximately around 142.05 grams in 1 mole. So we can go ahead and start setting up the problem. So I can take my given of 450 grams of the Na2SO4. Because I'm starting with mass, grams, that 142.05 will need to go in the bottom, and 1 mole would be the top portion of my conversion factor. So the last piece needed to solve this calculation then is we need to make sure that moles can cancel out, and we need to convert to molecules. So I can go ahead and eliminate my grams, so the conversion factor will rely on Avogadro's constant. So 1 mole will go in the bottom, 6.022 times 10 to the 23rd. MQs for molecules will be the top portion of our conversion. So again, you have two different ways you can calculate this. You can divide, then multiply, or you can do the multiplication first and then the division step. Again, to 2 decimal places, I got 1.91 times 10 to the 24th molecules of sodium sulfate. So this is very similar to the first example. If you take a look at your conversion factors, you use the same 2 pieces of information. It was just put in reverse. So you have one last example that you worked through, and this is much like example 1 in that we're starting out with a representative particle. Example 1 started with atoms, this one is starting with molecules. So our given is going to be that 3.30 times 10 to the 23rd molecules of this dinitrogen hexaiodide. So in order to make those molecules cancel, if you take a look at your roadmap, that's going to rely on Avogadro's constant. And therefore the top portion of the conversion factor is going to be the mole, and you can eliminate those out. So it wants grams, so then you should realize that you need molar mass. So we have a formula of N2I6. So you have 2 nitrogens to inventory and 6 iodine. Looking up each of their individual masses, nitrogen is 14.01. Iodine to 2 decimal places is 126.90. So this is going to give you a relatively large molar mass. So when you multiply and add them up, you get 789.42 grams per mole. So again, looking at setup, the bottom portion of your conversion factor in the last piece should be the mole, and the top piece should be the mass of 789.42. So you can go ahead and multiply and do your division step, or again, division by multiplication. I got an answer of 432.59 grams, and this is of the N2I6. Again, if you have any questions or concerns on your answers, if there's a rounding issue or whatever, please reach out to me. And so then you just have your worksheet to complete today. Again, you can print it out or write it out and upload a photo, or you can type it up within the Google Doc. Whichever you prefer works for me. Again, reach out to me if you have any questions.